Hi there. So we're up to chapter 3.4 on the normal distribution today, and I'm going to roll up into two sub-chapters in the book into just one video because I think they link very closely indeed. So this lesson is almost two lessons rolled into the one. So if it's fairly hard going, that will be why. But if you do your best to understand it and follow through this as a whole video lesson, you should get quite a bit of benefit from this and see that actually doing it in one may well be more efficient and will actually help you understanding better as well. So I'll talk you through what's going to happen today, but first of all I've got 4 warm-up questions for you as follows. Now, some of the stuff we're going to do today will link to the coding we looked at in year 12 of the statistics. So questions 1 and 2 are just there to remind you of coding, which hopefully you should remember from year 12, but you can be forgiven if you've forgotten. And 3 and 4 are just questions on different topics. So without further ado, let's now have a look at how we do question number 1. So question 1, we've got a data set M of 5 different values. So if we're all into 6 millions, for part A we need to code them into a data set called N, where each N takes each individual big M, takes away 6 million and divides by 100. So we need to do that and then write down the data set of N. And so all we're doing here is subtracting 6 million from each of these and dividing by 100. So 6,200,000, take away 6 million, just leaves us with 200. 200 divided by 100 is 2. And in a similar way, all of these values will shrink very nicely. So that becomes 300 divided by 100, which is 3. That becomes 3 as well. That becomes 5. You can do this on a calculator if you want to, of course. And 6,700,000 minus 6 million, then divided by 100, leaves us with 7. Part B, we need to calculate the mean and standard deviation of the coded data N. So the coded mean will be mu subscript N. Now obviously you could just add these together and divide by 5, but I'm just going to take the opportunity to remind you how to do this on the ClassWiz calculator. So what we can do here, we get the calculator up and ready, we press menu, then we can press option 6 for statistics, then one variable distribution, so press 1 for one variable. Now we just type in our n's as 2, 3, 3, 5 and 7, so 2 equals 3 equals 3 equals 5 and then 7. So we press option and go to one variable calculations. So press option 3, then mu, which is the same as x bar, is 4. So the mean of this coded data is 4, and the standard deviation of the coded data N is given by this symbol here, sigma x. And so I'll give this to 3 decimal places, that's 1.789. Now for C, we need to calculate the mean and standard deviation of the original data. So what's mu M and what's sigma for M? So hopefully remember how to do this based on the coded data, but if not, what we can do is just return and type in these values freshly. So for original data, instead of 2, the actual original value is 6,200,000. Press equals. The next one was 6,300,000. In fact, we had that value twice. So 6,300,000 again. Then we've got 6,500,000. And finally 6,700,000. Now we press option and one variable calculation again, and we can now see the mean of these is 6,400,000. And the standard deviation of the original data is not 1.789, but actually it's 178.9. Like so. Now for part D, this is just a way to remind you of how the coded data and the original data link to these values here, linked to how we've coded it. So using the answer to C above, so we can complete the following expressions for mu n and sigma n in terms of mu m and sigma m. So if m is coded to n using n equals m minus 6 million divided by 100, then the mean of the coded data, n, well, we got it was 4. So how does that compare to 6,400,000? How does 4 compare to this and these values here? Well, hopefully you can see that all we do to go from the mean of the original, mu n, to this one, is we subtracted 6 million from it. So subtract 6 million. And then we divide by 100. Bit of a mess there with my line. Hold on a second. So I'll divide that by 100 in a moment. That's what you get when you don't make the boxes big enough to do what you want. And this one, the standard deviation of the coded data, we'll compare this value here to the original. All we've done to go from this value to that one is divide by 100, and the significance of 100 is that that's what we divided the coded data by in the first place. So we just take the standard deviation of m and just divided it by 100. So the significance of that is that this 100, we end up dividing the mean by that and the standard deviation of original by that. But in terms of finding the standard deviation of the coded data, the standard deviation is not affected by shifting all the values up or down. So by subtracting 6 million to all values, that only affects the mean. This value here does not affect the standard deviation in any way, shape or form. So warm-up question 2 is going to use warm-up question 1 to help us. So for warm-up question 2 now, we've got a data set, big X, is coded using this following formula. So it's coded into big Y, where big Y is big X minus 60, all divided by 10. So we can use what we found from question 1 to work out the mean and standard deviation of Y. So the mean of Y, based on what we did from warm-up question 1, that's just going to be the mean of X minus 60 divided by 10. The mean of X was 60, like it says. We're also subtracting 60, so that's going to be 60 minus 60 divided by 10, which you can see is just going to be 0. And standard deviation of Y, well, to get the standard deviation of Y, we just take the standard deviation of the original data, big X, and we divide by what we're dividing it by in the coding, which is 10. But here what we're doing, we're dividing by 10, but the standard deviation was 10. So if we take any value and divide it by itself, then that'll just give us 1 each time. So 10 divided by 10 equals 1. So if the mean is a certain value, in this case 60, and we subtract that from the original values, and the standard deviation is a certain value, and then we divide through by the standard deviation, you'll see that of the coded data, that'll transform the mean of the coded data into 0, and the the standard deviation of the coded data into 1. So in general, we can generalize here in part B. So if you've got a data set A with mean mu and standard deviation sigma, if it's coded into B like so, then you'll always have that for the coded data B, that the mean of B, because you're taking away the mean from itself, the mean will go to 0, and the standard deviation of B will be 1. And so this is the key idea we're going to use today of how to code the normal distribution, in effect, into a standard normal distribution with a mean of 0, standard deviation of 1. You code the values like so. For each value in the norm distribution, you subtract away from it the mean of that norm distribution and divide through by the standard deviation of that normal distribution. We'll see this a bit later on today. Question 3. John works in sales and he assumes each sales call he makes is independent and knows from past experience that there is a probability of 0.1 of a call being successful. So he makes 20 calls, show that the probability of at least 4 of these calls being successful is 0.133, correct to 3 significant figures. Well, let's just think about what this question's saying first of all. He's making calls, there's a known number of calls he's making, 20, there's a 0.1 chance of a call being successful, and he's assuming that each call is independent. So a call is either successful or not successful, so this is building up into a picture that the binomial distribution would be appropriate. A call is either successful or not, there's a fixed number of calls, each call is independent of the next one. So we can say here, big X, we can model this as binomial. Now it's 20 calls per day, probability of any one call being successful is 0.1. 20 calls, so n is 20. Probability of a call being successful is 0.1. We want to find the probability of at least 4 being successful. So we have the chance of big X being at least 4. Now with the cumulative binomial probabilities, that only works when the probability symbol's facing the other way. So the probability of 4 or more being successful, that's every possible scenario apart from the probability that 3 or fewer are successful. So if we take away the probability of only 3, 2, 1 or 0 being successful, that will leave us with a probability of 4 or more being successful, which is what we're wanting. So how do we do this? Well, we need to press menu, go to option 7. Here, because we've got an inequality symbol, that is implying we need binomial CD. So you scroll down to binomial CD, press option 1, go for variable, which is option 2. Now we're wanting, for this one, to work out the chance of no more than 3 from 20 being successful, where the probability of success is 0.1. Press equals and equals again. That gives us 0.8670. So we've just worked out this probability, which gives us that. So the probability we're after is 1 subtract this one. So I go menu 1. 1 minus the answer I've just got is, as you can see, to 3 significant figures, 0.133, like we needed. Lastly, question 4, which relates to question 3. So here we have John, again, he's going to make 20 sales calls in a full working week on 6 days, Monday to Saturday inclusive. So we're going to use the answer to question 3 to calculate the probability that John makes at least 4 successful calls on exactly 2 of these 6 days. So this is actually a modified distribution of question 3. So if question 3, we had a distribution of X, where X was the binomial distribution of his successful calls out of 20 for one day, which was this, then we need to think about a different distribution now, Y, which will model his successes over 6 days rather than just for one. So what we need is something like this. So we need Y to be the distribution of the number of days out of 6 that 4 or more successful calls are made. So in other words, Y again will be binomial, because either you have a day where at least 4 are successful or not, so it's still binomial. But this time, from Monday to Saturday, that's 6 days, and from question 3, for just one day, the chance that 4 or more calls are successful, we worked out was 0.133 to 3 significant figures. So now what we need is the probability that John makes at least 4 successful calls on exactly 2 of these 6 days. We have a probability that we observed value of number of successful days is going to be 2. Not more, not less, exactly 2. Now for this one, because it's not an inequality symbol here, we need to use binomial PD. So we go Menu, Option 7, Binomial PD, Option 4. Press Variable. Now we want to work out exactly 2 out of the 6 days being 4 or more successful calls. And the chance of just one of those days being successful calls in terms of 4 or more successes from question 3 we had was 0.133. So we type this in, press equals, and then equals again, and we see that to 3 significant figures, it's 0.150 chance. That's question 4 completed, and therefore we should be fully warmed up. So let's have a look about what we're talking about today, which is using the inverse normal distribution to calculate probabilities. Probabilities, in fact, that use something which we're going to introduce called the standard normal distribution. So, what is the standard normal distribution? Well, this links to warm-up question 1 and question 2. So it's useful to standardize normally distributed random variables using coding. So the standard normal distribution has a mean of 0 and a standard deviation of exactly 1. So to code any normal distribution into the standard normal distribution, here's the process. So if big X is a general normal distribution with a general mean mu and a standard deviation sigma, then we can code this big X into the standard normal distribution, which is given by big Z, using this formula. So we just take each data element in big X, subtract the mean from it, and then divide all values by the standard deviation. And as you saw in warm-up question 1 and 2, that will give you a mean of 0 and a standard deviation of 1 once it's been coded. So because X is normally distributed, the coded data Z will also be normally distributed too. The resulting Z values, as they're known, will have a mean of 0 and a standard deviation of 1. So this is what the standard normal distribution would look like. So the standard normal distribution, Z, is a normal distribution, obviously, duh, with a mean of 0, standard deviation of 1, and this symbol here, which is called phi, capital Phi, a Greek symbol, this symbol just denotes the probability that the standard normal distribution will be up to any value A. So for example, if you've got a value A, you want to work out the probability of a value falling on A or less in the standard normal distribution, then that probability is given as phi A, which is one of the same as a probability of a standard normal distribution being less than this observed value A. So that's a bit of new terminology you need to remember. This isn't actually working out anything apart from just saying this is what the probability is. So this is a different way of writing the probability for a standard normal distribution. It'll all become clearer when we have a look at some worked examples. So let's do that now. So we have a random variable which is normally distributed such that X is normal with a mean of 20, standard deviation of 5. Write in terms of phi Z for some value of Z, this. The probability that big X is less than 17. So what I'm going to do here, I'm just going to remind us of what we had from before. So this is the standard normal distribution. Now what I've got here, I'm going to compare, and I suggest you do the same as well until you get very fluent and confident with standardizing the normal distribution. I'm going to assume to you that the best procedure is to do 2 separate distributions. The original one, which is going to be big X, like so, and then another one, which is going to be the standard normal distribution, big Z. So if I just do another one over here, then you can actually see firsthand what the coding's doing. So now, Z, normal distributed, 0, 1 squared. So for this original data, the mean is 20. We're trying to find the probability of being 17 or less. We're trying to find this value in the tail. So the coding to go from a general normal distribution to a standard is we take each value, in this case we take that 17, we subtract the mean, so we're going to subtract 20 and divide by the standard deviation. That's always how we code to get to the standard normal distribution. We subtract the mean, try to pick a different colour. We subtract the mean and we divide by the standard deviation. So the mean becomes 20 minus 20 divided by 5, which is obviously still 0. And what we're trying to find still is this yellow area here. So this value of 17 relates exactly to this value over here on the standard normal distribution. So what it's worth us just doing quite quickly is thinking, well, what is this value going to actually be? So 17 minus 20 divided by 5, that would be minus 0.6. So therefore what we can say here, the probability of x being less than 17 on our original normal distribution, that's one and the same as us saying we want the probability of this standard normal distribution, big Z, taking this value here or less, which is minus 0.6. And then if we compare this to that, we can write this in terms of phi by saying that's the same as phi of minus 0.6. So that's 1a done. We just rewrite this in terms of phi and then we're done. So if you actually did want to work that out and work out what this area would be, then you could actually use a standard normal distribution on the calculator now to work out what this would be. Even though the question isn't asking you to do this, I'll just show you how you'd relate this to actually generating the probability. So what we'd do here, if you needed to, you'd press menu 7, then we go to normal CD. Now I'd want our upper limit to be minus 0.6, our lower would be unbounded. So the upper would be minus 0.6. Sigma is 1 for the standard normal, mu is 0 for the standard normal, press equals, and we get this, 0.274. Now if you compare this to what we'd have for the original data, where the standard deviation was 5, and the mean was 20, but in this occasion we wanted to find the upper value being 17, and you can see we get exactly the same probability. So that's just me showing you that the standard normal distribution gives you the exact same probabilities, but it just takes out some of the variables. It makes everything into a standardized form, which is why it's so useful and so powerful. Let's have a look at part B. So part B, using the same distribution, where it's normally distributed with a mean of 20 and standard deviation of 5, we now want to work out the probability of this distribution taking a value of 22 or higher. So again, just to remind you of what we had from before, we want to be thinking of it in terms of this. So let this one be our initial distribution, 20 and 5 squared. Then we'll make our standard normal distribution from that, where it's going to be 0 and 1 squared. So again, the same way, that was 20. This time we're talking about being 22 or higher. So over here we're trying to find this value, like so. Now we standardise that. The mean's going to become 0, and this 22, like all values, we take the value, we subtract the mean, in this case 20, and divide by the standard deviation, which is 5. That's always how we code to get to the standard normal. And again, the same way though, we want to find this region here. So therefore, the probability of x being 22 or greater, that's the same for our standard normal distribution that we've got here. That's the same as we're trying to work out this one over here. So that's the same as the probability of z being 22 minus 20 over 5, that or higher. However, as in normal distribution questions, we need the probability symbol facing the other way. So that's the same as 1 minus the probability of z being down on this end, 22 minus 20 over 5. Because we always want this inequality symbol facing the other way. Now at this stage here, we could actually work out what 22 minus 20 over 5 is. Well, 22 minus 20 is 2. 2 divided by 5 is 0.4. So I can call that 0.4. And just as we had here, that, which relates to this, can be called phi of this value. So final step, I can just say that's the same as 1 minus phi of 0.4. So that's how we code into the standard normal distribution. Now we're going to have a look at some uses of this, some applications where we can actually use this standard normal distribution to find the original mean, the original standard deviation, or in some cases even both. So let's have a look at some more advanced worked examples now, 3 of them to be precise. So like I said, let's have a look at an example where we don't know either a mu or sigma. So this example here, we need to find mu. So random variable big X is normally distributed with unknown mean mu and a standard deviation of 3. We're told that the probability that big X is 20 or more is 0.2. From that, we need to find the value of mu. So again, what we need to do is remember what's come before. So this is the standard normal distribution. So I'm going to suggest we think about this original distribution and then code it to our standard one as well. So this is our original one, where it's normally distributed, mean mu, standard deviation of 3 squared. And over here, we've got the normal distribution, the standard normal distribution. So as long as you remember the coding procedure, where we just subtract the mean and divide by the standard deviation, that's the main thing. So that's mu. Over here, mu turns to 0. And we're told that the probability of our original variable being 20 or more is 0.2. So that'll be 20 here. And the chance of 20 or greater is 0.2. So let's add in what we have to begin with. So that's 0.2. In terms of our coding, this value of 20 will be coded to 20 minus whatever the mean is, because it always minus the mean, and then divide through by the standard deviation, which we do know that's 3. So that's how we code always. And this here, again, will be 0.2 of a curve on the standard normal distribution. But now we can think about solving this now. Okay, so what this is saying for the standard normal distribution is that the probability of z being more than 20 minus mu over 3 is obviously 0.2. This inequality symbol is facing the wrong way, so what we could do with working out is this area over here to the left of this line. If this is 0.2, then the probability of z taking a value of this or less will be 0.8. The probability of z being up to or including 20 minus mu over 3 equals 0.8. So now we know the probability, we need to find the value, so this is the inverse normal function. So if we use the inverse normal function now, we can work out what this value needs to be. So because we're using the standard normal, we're going to go menu, 7, inverse standard normal as it were. We want the area on this bit here to be 0.8. So we type area to be 0.8. Because we're talking about the standard normal distribution now, the standard deviation is going to be 1, and the mean now is going to be 0. So press equals and equals again. The value we need for that is 0.84162. So therefore, this thing here needs to be 0.84162. I've got the numbers already. 84162. So now we can solve this fairly easily, to be honest. This is like a GCSE question now. We've done all the hard work. So we need to have mu on its own. And so what we can do is we can multiply both sides by 3. We then get that 20 minus mu is this value here multiplied by 3. So if I go to menu, back to option 1, I've got this answer stored. So just multiply that by 3, 2.525-ish. Therefore, rearrange this. So add mu to both sides, then do 2 minus 2.525. So in other words, 20. Subtract that answer. We get that the mean must be 17.48 to two significant figures. In this worked example, now we're trying to find sigma, whereas before we were trying to find mu. But hopefully you'll see this is pretty much the same question, just trying to find a different parameter. So this time we've got a machine making metal sheets with width W that are normally distributed such that the widths follow a mean of 50 and some unknown standard deviation, sigma. So the variance is sigma squared. We're told that the probability of a width of any sheet being 46 centimeters or less is 0.2119. We now need to find the value of sigma. And for B, we need to find the 90th percentile of the widths. So again, we can start this off in the same way, just by reminding ourselves of what comes before. And again, what I'm going to do is have this as our starting original distribution, and we can see this being coded step by step to the standard normal distribution. And so this is W, which follows a normal distribution 50 sigma squared, whereas this is a standardised normal distribution, which has a mean of 0 and standard deviation of 1. So here we had that the probability that the width was 46 or less was about 20%, so this is in the lower tail somewhere. So that's 46. The mean is 50. And this little bit of a curve is 0.2119. So now imagine this being coded to our standard norm distribution. So if we take this and move on to here, then the mean obviously will always become 0 for the standardised normal, and all other values, well, including the mean as well, we take the original value, in our case this is 46, we subtract the mean from it, and divide through by the standard deviation, which we don't know, that's sigma, which we're going to find. And again, that's always how we code it. Because this is a 0.2119 proportion in our original distribution, it'll still be the same proportion in our standardised normal distribution. So that's still going to be 0.2119. So, for part A, what we need to do here is translate what we had from the original distribution to the standardised one. So we're told that the probability of being 46 or less equals 0.2119. Therefore, in terms of the standard norm distribution, that's the same as us saying probability of it being this or less, which is 46 minus 50, divide by the standard deviation, which we're trying to find. That must be 0.2119 as well. So now we can find what this value needs to be using the inverse normal function. So I'm just writing here what we're doing, so you can follow this. So using the inverse normal, call that a function instead actually. Then we can work out what 46 minus 50 divided by sigma needs to be. So what we do, press menu, option 7, inverse normal, option 3. And now we want the area to be 0.2119. Standard deviation is 1. Mu is 0 because we are talking about the standard normal distribution now. So what value will give us that required area? Well, the value we need apparently is minus 0.7998. So what we can do here, we can multiply both sides by mu. Sorry, by sigma, I mean to say. So 46 minus 50, that just gives us minus 4. That's going to be minus 0.7998 lots of sigma. Therefore, if we just divide both sides by minus 0.7998 and so on, we can work out what sigma is. So sigma is going to be minus 4 divided by this answer here. So minus 4 divided by my answer. I see that sigma is almost exactly 5. I'll call it 5.00 in fact. Now for part B, I need to find the 90th percentile of the widths. So what I can do here for part B is actually go back to the original distribution. So for part B, what I can do is I could use a standard normal distribution or the original, in fact. Either is fine. But now I know this is 50. And I also know that the standard deviation now is 5. So I'm trying to find the 90th percentile, which, as you should remember from year 12, the 90th percentile is the particular point where we get up to 90% of the data. So in other words, that's going to be 0.10. The stuff before is going to be 0.90. So all this in green is going to be 0.90, as in the 90th percentile. Making a mess of colouring this in. So anyway, using this value for sigma, I can now go menu, option 7. This time I need just the normal CD function. So press 2 for normal CD. In fact, no, because we're wanting to find a value which gives us a probability, it is inverse normal. So we're wanting this point here, which gives us 90% of a curve. So the required proportion is 0.90. Sigma is the answer we had from before, about 5.00. And the mean is 50. So press that in and equals again. We get 56.4. So the 90th percentile is 56.4. And that's all it is for that question. So the final one's going to be a bit harder, but then we're done. So let's have a look at the next worked example. Finally, to finish, worked example 3 for finding mu and sigma. So this time we've got a random variable x with an unknown mu, unknown sigma, but we are told two different things. We're told the probability that the distribution taking a value of 35 or greater is 0.025, and also probability that taking a value 15 or less is 0.1469. Based off these two values, find the value of mu and sigma. So again, just reminding ourselves what we had before, we've got this scenario here. So I'm going to take this as the initial normal distribution x, and then we'll copy across and think about what the standard normal distribution would be. So first of all, like I say, I'm going to say this as x with the unknown mu and unknown sigma, but it gets transformed to this over here, which is the standard normal, with of course a mean of 0, standard deviation of 1. So what we're told first of all is the chance of the original distribution being 35 or greater is very small, 0.025. So that's 35. And this probability here is just 0.025. And as well as that, we're told about it being 15 or less. So that's 0.025. The chance of being 15 or less is 0.1469. So that's going to be at the other side of the mean. That's going to be down here somewhere. And that's going to be 0.1469 like it says. So we can now transform this into the standard normal. But before we do that, what we can say here is the probability of x being 35 or greater, we're told that's 0.025. So we can get this into the right standard form. In other words, the probability of x being up to 35 would be 1 minus 0.025, which gives 0.975. So that's a more useful value to be using. So saying this is equivalent to saying this above here. So that's the equivalent thing I'm saying. And of course, this one here, probability that x is 15 or less is 0.1469. So when we code this to the standard normal, then this value here, again, we always subtract the mean, which is unknown, so that's 15 minus mu divided by sigma. Like so, and of course that will still give, even on the standard norm distribution, the same proportion of the curve, so that's going to be 0.1469. Whereas at the higher end, where this was 35, that goes to 35 minus mu divided by sigma, and that's 0.025. So now we can think about how this codes. So if we have a look at this one here, where it's 35 or less on the normal, on the original normal distribution, then we can take this and compare this to the standard normal distribution counterpoint, which is this value here. So the probability of x being, sorry, not x because it's normal, the standard normal now is z, z being less than 35 minus mu over sigma, has to be less than 0.975. And from that we can now use the inverse normal function. To work out what value we want 35 minus mu over sigma to be to generate this required probability. So what do we need 35 minus mu over sigma to be? So what we do, we go into inverse normal. We want an area of 0.975. Sigma for the standardized normal distribution is going to be 1, and the mean is 0. So press equals and equals again. So we need, for that one, 1.95996, approximately. 1.95996. Whereas for this one, again coding it to the standard normal, we're wanting the probability of z, again 15 codes to 15 minus mu over sigma for the standard normal, we're wanting that to be 0.1469. Okay, so that's where the probabilities are coming from. And again, the same way, we can use the inverse normal function to find this one, the required value of 15 minus mu over sigma. And that'll tell us that 15 minus mu over sigma needs to be, well, let's see. So again, now we want the area to be 0.1469. So that gives us minus 1.04982. Just check those values are correct. 04982, yes they are. So what I've got here is a pair of simultaneous equations to solve. So all we need to do now is to solve these simultaneously, and then we're good to go, and we've done. So just taking our time with this, I'm just going to solve these simultaneously. So first of all, if I multiply through by mu for both of these, so I multiply through by sigma, I mean to say. This one here, we get 35 minus mu equals 1.95996 sigma. And this one, if we multiply through by sigma, I get 15 minus mu equals minus 1.04982 sigma. So from this one, if I rearrange to find what mu is, I can see that mu must be 35 minus 1.95996 sigma. And if I make this one here mu the subject, I get that mu must be 15 plus 1.04982 sigma. Now because both these are equal to mu, I can set one equal to the other. So I can therefore say that 35 minus 1.95996 mu equals 15 plus 1.04982 mu. So I can just set this equal to the other side. I can set that equal to that. So 35 minus 1.95996 mu equals 15 plus 1.04982 mu. So now if we get all the mu's onto one side of the equation, so if we add 1.95966 mu and also subtract 15, then what that'll give us, on this side 15 take away 15 is 20, and we add this to both sides, we're going to get 1.04982 mu, so I'll just take this value here, times by minus 1 to get it to be positive, like so. So I'm going to add on to that 1.95966, so plus 1.95966, I get this, 3.00948. Therefore, dividing both sides by this value of about 3, therefore I get the sigma 20 divided by that answer, so 20 divided by that answer just stored. I get there that my value of sigma must be 6.65 to 3 significant figures. And now I've got that, I can now substitute that back in to find mu. So now I know what sigma is. Sigma is this. I can sub this into sigma here, for example, to find what mu is. So therefore, mu, the mean, is going to be 15 plus 1.04982 lots of 6.65-ish, whatever answer I've got stored. So just take this here, 6.65 as it's stored. I'm going to multiply that by 1.04982. I'm going to add 15 onto that. I get 21.97. So to 3 significant figures, that's 22.0. and finally we're done. So it actually came out to just be a simultaneous question problem, this one. But now, as ever, you need to try some on your own. So, because this is quite a bumper exercise, I want you to try exercise 3D first, the whole lot of it, on page 49. And once you're comfortable with those, you should be able to have a go at page 51 and 52, all of exercise 3E, which is working out unknown means, unknown standard deviations, or both, like in that last example. So, as ever, each time you do a few questions, check them regularly, make sure you're understanding and be self-assessing. And if you're not sure, then please do ask me. So once again, thanks for tuning in. Please do like and subscribe, and please do stay tuned for the next one in the series. So until next time, take care, and goodbye for now.